understand why elements behave the way they do, we have to look at the atom in two distinct parts. First, the outer electron cloud, which dictates how atoms bond and react to form the chemical building blocks of our world. Second, the heavy, dense nucleus at the center, which governs stability and radioactivity. Mapping that electron cloud requires three core rules. The Aufbau principle tells us that electrons fill the lowest energy orbitals first, following a strict diagonal order. The Pauli exclusion principle states that a single orbital holds a maximum of 2 electrons, and they must have opposite spins. Finally, Hund's rule dictates that electrons will fill equal energy orbitals singly before they start pairing up. Let's apply these rules to sodium, which has an atomic number of 11. We place 2 electrons in the 1s orbital, 2 in the 2s, and 6 completely filling the 3 2p orbitals. That leaves exactly 1 electron remaining, which goes into the 3s orbital. Our final configuration is 1s2, 2s2, 2p6, 3s1. That single, lonely electron in the outermost 3s subshell explains sodium's behavior. Because it easily loses that 1 electron to reveal a stable, full inner shell, sodium acts as a highly reactive group 1 metal. When we move to the heavier transition metals, the rules require a slight adjustment. Take iron, atomic number 26. When iron forms a positive ion, you might expect it to lose its highest energy, 3d electrons first, but it actually loses its outermost 4s electrons before the 3d electrons are touched. To form an Fe2+ ion, those two 4s electrons are stripped away, leaving a stable 3d6 arrangement. There is a strict exception for neutral atoms like chromium and copper. Based on the standard rules, you would expect copper's outer shell to be 3d9 4s2, but a completely filled d subshell provides extra stability that overrides the normal filling order. We strike out the expected version because 1 electron shifts, making the actual outer configuration 3d10 4s1. Now, take a moment to write out the full electronic configuration for a neutral copper atom, keeping that stability rule in mind. The correct full configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. Mastering these specific shifts allows you to accurately predict the complex oxidation states of transition metals in industrial chemical reactions. If we move past the electron cloud and into an unstable nucleus, we encounter radioactive decay. Nuclei shed excess energy by emitting 3 main types of ionizing radiation. Heavy alpha particles are easily blocked by a simple sheet of paper. Fast-moving beta particles require a layer of aluminum to stop them, and high-energy gamma rays carry no mass or charge, requiring thick concrete or lead to reduce their intensity. When an atom undergoes beta decay, a neutron in the nucleus turns into a proton, emitting an electron. Because a proton is gained, the mass number stays the same, but the atomic number actually increases by 1. Carbon-14 decays into nitrogen-14, shifting its atomic number from 6 up to 7. This graph plots the count rate of a radioactive sample over time, illustrating a smooth exponential decay curve. Because decay is a random but predictable process for large samples, we can calculate a specific half-life, the time it takes for half the nuclei to disintegrate. The half-life is equal to 0.693 divided by the decay constant, lambda. Let's apply this to a real scenario. A Ugandan hospital has 1,200 becquerels of a medical isotope with a 6-hour half-life. Pause the video and calculate how long it will take for the activity to drop to 150 becquerels. The activity halves from 1,200 to 600, then to 300, and finally to 150. That is 3 complete half-lives. 3 multiplied by 6 hours gives us exactly 18 hours. By calculating precise decay constants and half-lives, medical physicists can deliver exact doses of radiation to target tumors without causing excessive tissue damage. The behavior of electrons moving between orbitals dictates how we design lithium-ion batteries and solar cells. Meanwhile, the precise mathematics of nuclear equations guides the sterilization of agricultural exports and the planning of medical radiotherapy. Here are the critical rules to retain. follow the Aufbau diagonal for base configurations, but remember that transition metals empty their 4s subshell before their 3d subshell. In nuclear equations, always balance the mass and atomic numbers, and use the 0.693 constant to relate half-life to the rate of decay. Mapping the electron cloud allows us to engineer new chemical compounds, while measuring nuclear decay lets us harness radiation safely. For more step-by-step practice and competency-based resources, visit Yaka Digital Network at yaka.cc. Keep practicing, and we'll see you in the next lesson.